Hello, we have seen how Maxwell was able to unify electricity and magnetism into electromagnetism by adding the displacement current to Ampere's law. And then he could also use these new unified equations to derive electromagnetic waves. And so let's look at how he did that. For that, let me again share my slides here. Alright, Maxwell, as I just said, was the first to understand that light is an oscillation of the electromagnetic field and was able to predict that electromagnetic waves can also exist at any frequency, not just the frequencies corresponding to visible light, which is just a tiny sliver of the entire electromagnetic spectrum. That also includes, for example, the wavelengths of radar used in installations to track rockets and missiles. But of course, there are countless applications of this. Maxwell really enabled all the applications of radio waves and so on. Alright, we have seen Maxwell's equations before, and in general there is Q inside over epsilon naught, and there's another term for the physical current through an enclosed surface in Ampere's law. But if we limit ourselves to a region of empty space, empty of any charges that can cause an electric field and empty of any charges that can make a current flow, then Maxwell's equations take on this simple structure that now really looks very symmetric between electric and magnetic fields. So we have Gauss's law both for the electric and magnetic field, we have Faraday's law, and we have Ampere's law with the Maxwell addition of the displacement current and the absence of any physical current. Alright, so the idea now is that a changing magnetic field creates an induced electric field and vice versa. And so if a changing magnetic field creates an electric field that in turn happens to change in just the right way to recreate the original magnetic field, then the fields can exist in a self-sustaining mode, kind of shown in this cycle. The changing electric field induces a magnetic field that's changing as it's getting induced, and hence again inducing an electric field, and so on. And so what would that look like? Well, let's suppose we have an electromagnetic wave that's propagating along the x-axis. It's not just a point beam of light, but it's a wavefront in three-dimensional space, and so at any instant in time that wavefront is a plane in the yz plane that's advancing along the x direction. And let's take the electric field direction to be vertical along the y-axis and the magnetic field horizontal along the z-axis, and we'll see why they need to be perpendicular to one another as we derive the wave equation. So at any wavefront, at any instant in time, we have a constant electric field along any position in the yz plane shown here. for a constant x, and similarly a constant magnetic field at every point on this plane. We can take a different projection through our three-dimensional space, and so if we look along the x-axis, we see that as the field oscillates, the magnitude of those vectors becomes smaller along the x direction, may even change direction and then become larger again, and so on. So the field changes along the direction the wave propagates, both the electric and magnetic field. So that's the setup, and so let's see what Maxwell's equations tell us. Let's first consider a Gaussian box around some region of space with the faces of the box aligning with the principal axes of our coordinate system. Well, then it's easy enough to see that the electric flux through the box must be zero. Any electric field coming in from below exits above, and moving to the right along the x-axis we may have a different value of the electric field, but again any field line entering also leaves. And the same is true for the magnetic field, and so we see both Gauss's law for the electric field and the magnetic field are satisfied. The net electric flux and the net magnetic flux through this box are zero. This doesn't really tell us anything about the wave being able to exist, but it at least tells us that it's compatible with Gauss's laws. So that's a consistency check, no problems with Gauss's laws. But now we need to really use Faraday's law and Ampere's law to come out with the wave equation. And so let's first apply Faraday's law, and as Faraday's law relates a changing flux of the magnetic field to the electric field around a curve. Let's select a curve that is the border of this rectangle shown. The rectangle in the xy plane, so that the magnetic field is perpendicular to this rectangle. And then it's easy to determine the magnetic flux. It's just the z component of the magnetic field, which is the entire magnetic field strength. There are no x and y components of the magnetic field here, times the area of the rectangle, and the area of the rectangle is just its width times its height, delta x times h. And so then the change in that magnetic flux, well, our rectangle is of constant area, and so that just factors out of the time derivative, and our change of magnetic flux is just d bz by dt times h times delta x. Okay, now we need to worry about the other side of Faraday's law, and that's the line integral of the electric field around this rectangle. And so let's look at that. We have the same rectangle here again shown. Now on the top and bottom sides we are moving sideways, but the field is in the y direction. We are moving in the x direction or the minus x direction, but the field is in the y direction, and so the top and bottom edges don't contribute to the integral, to the path integral around this closed loop. The contributions of top and bottom edges are zero. Now along the left edge we have a constant field anywhere along this edge, and similarly on the right edge the field is constant, but it may be a different value, right? As we move in x, the magnitude of the field may be changing. So at this point it's useful to relate what the field on the right edge is compared to the field on the left side, and for that we just do first order expansion. So the field a small distance away from another point is going to be what the field is at this point plus z delta x times the slope of the graph, right? For a straight line this would be an exact expression. Of course here you can see if my graph curves over, I might with the slope here end up a little bit too high, or in another example too low, but as my delta x is very small, I end up with a better and better approximation, and our delta x is meant to be small. Okay, so the field on the right side is just the same as the field on the left side, plus this term involving the derivative of the electric field with respect to x. And so on the right side we are going upward, and that's the orientation of the field and how we go along the curve. So we have plus this expression times h for the contribution of the right side, and then we have on the left side we are going downward, the field still points upward, so we have minus h times e of x on the left side. And so we see the contribution of the left side and part of the contribution on the right side here cancel each other, and all we have left is h times this term here. So the entire integral consists of 0 from top and bottom, two terms on the left and right that cancel each other, and just this leftover term on the right that's written here. Okay, the field times the distance we integrate over h. And by Faraday's law that's got to be equal to the expression we found on the previous page, and so then we can divide out the area of our rectangle and find a relation between the change of the electric field with respect to position and the change of the magnetic field with respect to time. So let's keep this equation in mind. I'll refer back to that in a couple of slides. Before I do that though, let's also see if we can apply Ampere's law. And for that we again look at a rectangle, but this time in the horizontal plane, in the xz plane here, such that the electric field is perpendicular to our rectangle, and we get an electric flux, that's just the y component of electric field, which is identical to the magnitude of the electric field, times the area. Now you might argue we really should integrate over the area carefully, because the electric field may change as we move along x. And yes, you are right, but remember delta x is going to become small, and so how it changes is negligible in the limit of delta x becoming very small, and so it's just we can assume that Ey is constant here across our rectangle that's becoming a more narrow strip as delta x becomes small. Well, alright, what is then the time derivative of the flux? Again, the area of our rectangle doesn't change over time. We just think of it as a very narrow strip that's constant in time, and so only the field changes over time, so that's our one side of Ampere's law. And for the other side we argue about the integral of b ds around this curve in very much the same way that we've argued about the line integral for the electric field in the previous rectangle. So again we get two contributions that are 0, where the field is perpendicular to the direction our curve moves, and then we get two contributions that are almost the same but in opposite directions, almost cancelling each other out and just leaving a small contribution that's L times dBz by dx. And so then inserting the time derivative of the electric flux that we've also previously just looked at, we find, upon cancelling again the area of the rectangle, that we also get a relationship of the rate of change of the magnetic field with respect to position, and that relates to the rate of change of the electric field with respect to time. Alright, so now let's put it all together. Let me put those two equations, the one I just had on the previous slide and the one I had a couple of moments ago from Faraday's law. These are our two equations. So how can we combine these? They look complicated, right? We have two quantities, two equations for two different quantities, electric and magnetic field. Well, and there's time and position derivatives and so on. Well, let's see. If I take the first derivative, the first equation, and I apply a time derivative on each side, then I get this equation shown here. And if I take the second equation and I apply a position derivative on both sides, I get the second derivative with respect to position on the left side, and I get what I had on the right side with another position derivative inserted. Now, the order of differentiation doesn't really matter. D by dx times the d by dt of a function, when the function is well behaved, as we demand for anything that represents a physical quantity, is the same as d by dt of d by dx of that function. And so we see, if I just insert this over here, I just get, well, two minus signs that cancel, and I get, well, the left hand side, and on the right hand side I just get my constants and dBz by dt, and I guess I changed it around so that I have the time derivatives on the left side, and then this moves over so that I get the 1 over this constant times the dBz by dx squared. And well, if you remember the wave equation, this is the wave equation. The second derivative with respect to time equals the velocity squared of the wave times the position derivative, the second position derivative. So the magnetic field oscillates like a wave, and we can do the same for the electric field. So starting again with my first equation from Faraday's law and taking a derivative with respect to position now, I get dEy squared by dx squared, and that's the derivative with respect to time and position of the magnetic field. I want these to be looking similar, so I take a time derivative of the second equation, and then I recognize that the derivatives are interchangeable, so these two things up to the minus sign are the same, And so this here is equal to this here, the two minus signs multiply to plus 1. And then let me again change it around and divide this to the other side. I have the same term for the velocity squared and the wave equation also for the electric field. And so in summary, we combine these Faraday's and Ampere's laws to get wave equations both for the electric and magnetic field, where the speed of the wave is predicted to be 1 over the square root of epsilon naught mu naught. And these are constants we can determine in tabletop lab experiments. And yet, if we form this combination of these two constants, we get something that's experimentally in agreement with the speed of light. And so this is pretty convincing. Electromagnetic waves can exist with the waving magnetic and electric fields propagating through space. And this is what Maxwell did. And it matches the experimental speed of light. And so we find that there are electromagnetic waves with perpendicular electric and magnetic fields propagating through space. Initially, when this was discovered, people thought that maybe there's an ether, a medium for the electromagnetic wave to travel in, similarly to how sound waves travel in air and every other wave travels in a medium, waves propagating on a string or something like that. But it turns out really what's waving here for electromagnetic waves are the electric and magnetic fields, and we don't need any medium for the wave to travel in. It's just an electromagnetic wave that can propagate in free space. And so we'll look at properties of electromagnetic waves more in the next video. So that's it for this video. See you again soon.